Fatigue and a little look at recovery will wrap up our look at energy systems. So the SAC task for this will be a lab report where there'll be some data from various activities we've participated in, and we'll be looking at energy systems and fatigue. The only piece of recovery you really need to be aware of is active versus passive recovery. We go into a lot more different strategies in semester 2 for recovery. The key knowledge really just talks about the energy systems in connection with fatigue or limiting factors. I'm going to keep using that word, fatigue. We're also going to have a brief look at active and passive recoveries and the rates associated with the energy systems recovering. That's a really simplistic view of recovery. We've got a lot more to look at in Unit 4 when we look at enhancing performance and recovery strategies. In looking at fatigue in broad strokes and giving you some general classifications, we then drill down into peripheral fatigue, which is just a fancy word for fatigue that occurs within the muscle or the muscular system. The guiding questions again start at the very top level or macro level in terms of what is fatigue and the 3 subtypes, local, general, chronic. We then briefly just make sure we understand the difference between peripheral or muscular and thermoregulatory. And then we're going to unpack the peripheral fatigue into fuel depletion and metabolic byproducts. We'll certainly then pull apart lactate and play with my good friend LIP, lactate inflection point, before briefly looking at when we would use an active and passive recovery and what a good one would look like. So fatigue, if you had to define it, when the body can't perform at optimal level. Okay, so it can be talking about force, can be talking about power, can be talking about work output, but essentially your ability to work is compromised. Types of fatigue are pretty simple definitions there. Local just simply looks at one particular group of muscles or a particular body part. If you were doing 100 billion crunches, you'd have local fatigue in your abdominals. General is that whole body aching. So think of major movements, probably big sort of team sports or big physical activities. And then lastly, chronic, which is, as the syndrome's called, chronic fatigue syndrome, where you are well and truly not well. The causes of fatigue is where the nuts and bolts of this area of study need to be unpacked. And you can see there on the left, peripheral muscular is one, so anything that occurs within the muscle. Central is outside of the muscle, and in particular central nervous system and looking at all the neural stimulation. And then thermoregulatory is anything to do with a temperature increase or drop. In most cases we're looking at an increase, and dehydration plays a major role in that. The rest of this slideshow looks at the peripheral muscular causes of fatigue, and in particular fuel depletion and metabolic byproducts. In regards to peripheral muscular fatigue, there are 2 subheadings, and that's the depletion of fuel stores and the accumulation of metabolic byproducts. And importantly, remember that we're actually looking at the fatigue causing ones. So while there are other byproducts that are caused through energy systems, read questions carefully, because the 3 that are listed there are the only ones that actually cause fatigue or are linked to fatigue. So in terms of depleting the fuel stores, we're only considering PC and glycogen within the muscle because we're looking at peripheral muscular causes here. Importantly, ATP depletes, but it's not a fuel. And the other fuel we could consider is blood glucose, but because that's outside of the muscle, that's considered a central factor, although it does come under fuel depletion or depletion of fuel stores. So the metabolic byproducts that are listed here, ADP and inorganic phosphate, both coming from rapid explosive activities, and both are thought to inhibit or slow down calcium's entrance into the fibre and stopping the contraction process, the mechanical contraction process. ADP is also said to be in a delicate balance with ATP, so that if we're getting a greater accumulation of ADP than ATP that exists in the muscle will stop splitting. And lastly, hydrogens, which you know all about. They drop pH, increase acidity, inhibit glycolytic enzymes, that slows down the speed of glycogen splitting, and associated with fatigue in anaerobic events, and also above lip when there's an exponential increase of lactate and hydrogens. Just remember that lactate doesn't cause fatigue. So there's a little snapshot of fuel depletion for when PC would be particularly relevant. So something sub 10 seconds is the entire duration of the ATP-CP system, but PC actually we have about 6 to 8 seconds worth of fuel when we are working maximally. So power events, dynamic explosive events, you won't deplete fatigue. You won't deplete your CP with one shot put throw, but if you do consecutive throws over 10 seconds, you will, and that will lead to fatigue. So in contrast to the power events, we're now looking at the fuel depletion of glycogen, and that's within the muscle. Remember, a peripheral muscular cause, fuel depletion within the muscle. So typically we've got about 90 minutes worth of glycogen in our bodies, which might equate, depending on your running speed, to 25 kilometers of a continuous run. After which, if you are depleting your glycogen stores, or you have depleted them, your body must switch to a greater contribution from fats, which requires more oxygen, and therefore decreases force production and hastens fatigue. Be mindful of the fact that there's enough fat in our body to last for 120 hours at about 60% of VO2 max. So that's still working at a reasonable rate. I can't think of any sports where fat depletion is going to be a valid possible answer in your exam. Also be mindful that not all endurance athletes or people that work for 91 minutes must hit the wall. Due to chronic adaptations of aerobic training, nutritional status, diet, health, illness, genetics, all those kinds of things, you can prolong, or glycogen spare, you can prolong your use of fats earlier in the work bout, such that you save carbohydrates for later in the work bout. So you don't have to hit the wall just because you exercise for longer than 90 minutes. And finally, glycogen is never 100% depleted. You've always got some, but it's just that your body can't really use it. And just a final reminder that a drop in blood glucose, while it's fuel depletion, is a central mechanism because it occurs outside of the muscle.
Another term that's really important for you to grasp is this idea of hitting the wall. If you play some YouTube clips for American cyclists, they talk about bonking. They mean hitting the wall. So this is different to glycogen sparing, but it's somewhat related in that when our body depletes the glycogen stores, which could be 60 minutes into a work bout, it could be 8 hours into a work bout if you're an elite Hawaiian Ironman, but typically we say about 2 hours worth. The body has depleted glycogen stores and it must decrease intensity because it cannot break down fats as quickly to restore the same amount of ATP. And we'll play a couple of videos showing marathon runners and iron women hitting the wall when literally they cannot work at the same intensity, so they start crawling or walking.
So we've looked at fuel depletion. The other go-to response for fatigue, particularly for peripheral muscle, is fatiguing byproducts. And you must remember that not all byproducts in breaking down chemical fuels for ATP are fatiguing. If you look at the aerobic pathway, for example, heat, carbon dioxide and water are considered non-fatiguing. Inorganic phosphates, in a nutshell, are thought to weaken muscle contractions. I don't think you'd be asked in any great depth to explain how that is the cause, but they are thought to contribute to fatigue by inhibiting calcium's role in getting the cross bridges to attach at the mechanical level within the muscle. Hydrogen ions we've spoken about in great depth, and I think you could be asked to respond to that. We're told that in terms of anaerobic glycolysis and lactic acid splitting into lactate and hydrogen ions, the hydrogen ions reduce the muscle's pH, which means we get an increased acidity in the muscle. And essentially, in terms of stopping the glycolytic enzymes to help that entire anaerobic glycolysis process, it slows down the rate of ATP resynthesis. ADP is probably even more obscure than looking at inorganic phosphates. And if you look at your textbook, there's a little response there, but essentially within the muscle, it's thought to somehow limit the transfer from the neural or electrical impulse into the muscle cell. So in wrapping up LIP in regards to fatigue, VCAR and the study design suggests that you are able to define the term, and something like the last point, which fits in nicely with the LP of LIP, the last point where lactate production equals its removal. Okay. On a graph, you simply use a ruler or your finger to see where the line departs from the straight. In terms of understanding what happens beyond LIP, basically it's the top rate of ATP resynthesis for aerobic restoration of ATP. So above LIP, you increase your anaerobic glycolysis contribution so that we get an exponential increase of lactate and hydrogen ions. Okay. Now, in terms of looking at various athletes, you can have a look here. The blue line here, at 4 millimoles of lactate, they reach lip, which is equivalent to working for 20 minutes, finishing at 12 kilometers an hour. In comparison, the purple line, athlete 3, he doesn't reach lip because there is no exponential increase in lactate production. So despite working at 45 minutes at 13 kilometers an hour, his reading is 4.2 millimoles of lactate per litre, but he hasn't actually gone up exponentially, so that's still relatively flat. So athlete 3 is clearly more aerobic. They will do better in this particular work bout because they haven't had to draw increasingly on anaerobic glycolysis. Clearly the impact of working above that is that your muscles increase hydrogen ion concentration, which decrease glycolytic enzymes, which decreases the speed of splitting glucose and glycogen, and will ultimately cause a reduction in intensity as the body cannot sustain that muscle acidosis that the hydrogen ions are contributing to. This graph here, again, if you put your ruler or your finger along that, you would see where it dramatically departs from the trend. So it doesn't necessarily have to relate to a figure of millimole in your blood, although they do talk about figures like 3 to 4 millimole is often where lip occurs. In most of the graphs you'll be asked to look at, you may not even have figures on it. So essentially, where does it start to go at right angles? Lactate inflection point, or lip, is the final point where the lactate that's being produced is able to be cleared. Now, it's really a measure of the efficiency of the aerobic energy system. Now, we know that through interplay we are getting multiple energy systems contributing to ATP restoration, but at lip we are not getting any of the harmful byproducts of hydrogen ions that we get through anaerobic glycolysis. If you are working at lip for a period of time, or certainly above it, the moment you step above it, you are unable to clear that lactate and hydrogen ions at the same rate they're being produced, and you will start to fatigue. And essentially what it means is that anaerobic glycolysis is contributing more or increasing its contribution at those work rates or intensities. We've seen various figures of where lip occurs. There's a rough estimate of maybe 90 to 94% of maximum heart rate. But essentially, in terms of your exam and your SAC, you would be asked to find it on a graph. And if you just use your finger or your ruler to hold over the trend in the line, the point where it moves drastically from a straight line, so there's an exponential increase, is lip.
Yet another graph image of lip, and while this axis gives you blood lactate levels on the vertical axis and running speed on the horizontal, you won't always have that data. It's not that significant to know points in time that it occurs, other than to know it's the last point in that line before it goes up exponentially. So of course we're talking about lactate because it's easier to measure in the blood than hydrogen ions, which are in the muscle. Because they increase in a linear fashion, we continually talk about lactate, but it's the hydrogen ions we're more interested in.
I put lactate production here. Lactate is a byproduct, but it's not a fatiguing byproduct. Interestingly, 3/4 or 80% of lactate that is caused when lactic acid dissociates as part of anaerobic glycolysis is actually returned to the liver and is then reformed into glycogen. And that term's called gluconeogenesis, so new creation or new birth of glucose or glycogen. And that's technical term is the Cori cycle or the lactate shuttle. That's all in your textbook. But it's pretty groovy to think that this lactic acid that once upon a time was scorned by athletes and media alike, it's not so much lactic acid, that's the problem, it's the hydrogen ions. Now we talk about lactate and we measure that, and we talk about lactate inflection point because it's easier to measure lactate levels in the blood than it is to measure hydrogen ion levels in the muscle. Because they both increase in a linear fashion and they have a relationship of increasing together, we measure the lactate as an indicator of hydrogen ion accumulation.
This may be of interest to you, but lactate levels, while they increase in response to high levels of activity, or high intensity, of activity, the highest moment for lactate, if it was measured correctly, would be within 3 to 8 minutes post-exercise of a very highly intense short duration work bout.
And that's because at the end of the work bout, the body is moving the lactate between muscle fibers, between muscles, to aerobically break down the bulk of it, about 80%, and the other 20% travels through the circulatory system back to the liver to reform into glycogen. So yes, it will increase during exercise, but if that lip graph were to continue, for example, the immediate 3 to 5 minutes after exercise would see even higher levels as the body is clearing the lactate from the muscle through the circulatory system back to the liver. So here's the basic side-by-side for recovery, remembering that we spend a full 6 weeks on this in Unit 4 when we look at nutrition, hydration, physiological, psychological, and a few other things, types of strategies to enhance performance and recovery. For us at this time point leading up to this SAC task, you just need to know the difference between passive and active recovery. And in terms of energy systems, it's only ATP, CP dominant work bouts where we would prescribe a passive recovery, and only because it is faster to restore ATP and CP. So all other work bouts that would draw on anaerobic glycolysis and the aerobic system are better suited to an active recovery to help remove lactate or restore it back to glycogen, to get hydrogen ions out of the muscle, and all those other things that happened with EPOC when we looked at that as part of oxygen deficit steady state. So steadily reducing heart rate, all those acute body responses, avoiding venous blood pooling, and bringing us back level and steady to what we were pre-exercise.
So the benefits of the active recovery, which is really in an effort for the athlete to prolong their EPOC, excess post-exercise oxygen consumption. So starting first and foremost with that restoration of ATP and CP stores, but not as quickly as a passive recovery. We then get to restore our body's oxygen in the hemoglobin of the blood and the myoglobin in the muscle. We get to hasten the removal of lactate out of the muscle via the circulatory system to the liver to reform glycogen. Remember the term gluconeogenesis. And obviously it avoids things like fainting and passing out with venous blood pooling. So the removal there of hydrogen ions and inorganic phosphates is also a benefit. So all of those things to do with chiefly anaerobic and aerobic energy systems are beneficial via an active recovery. So in looking at passive recovery now, all we need to know for this time of the year is the types of sports for which we would prescribe passive versus active. And the types of sports for passive are high intensity, dynamic, explosive, powerful type events, certainly sub 10 seconds, because that's the limit of the ATP-CP system. So it's faster to restore the CP bonds, and that's why we prescribe it for those types of exercises and events. You might also prescribe it if someone's absolutely physically exhausted. You're not going to tell them to go and run 3 laps if they've just finished an Ironman, although they should keep walking. Interestingly here, CP stores up to 70% can be restored within 30 seconds, but then it takes another 2.5 minutes up to 3 minutes to get 98%. And just be mindful, if somebody hasn't worked for 10 seconds, they don't need to wait a full 3 minutes to restore those CP bonds.
I'll give you a hard copy of this in A3 again because I've done the work. I get the greatest value out of this mind map. But it's got fatigue front and center in grey. It branches off to the right with thermoregulation, which is mostly heat. It can be also the cold. And then to the left, we're looking at peripheral muscular fatigue and breaking that further down into fuel depletion and accumulation of metabolic byproducts. I really like mind maps. If you don't, that's fine. But I find a really good way to call back to my mind's eye when I'm in an exam condition or under assessment conditions.